Hello, class. What we're going to discuss today is acids and bases. Now, who here's cooked food or made chocolate chip cookies? What's one ingredient that you have to add, or the cookies are going to just be flat and gross? You have to add baking soda. And the reason why we're adding baking soda is because it's going to help the cookies rise and get some volume. And the reason why the cookies rise is because the baking soda produces carbon dioxide gas. And so it helps to make the cookies rise because of the formation of the gases. Now what's happening with the baking soda is that it's reacting in an acid-base reaction to create the carbon dioxide. So acid-base chemistry is very prevalent in the food sciences and in chemistry and biochemistry. It's just everywhere where you have an acid and a base and they react. How many of you have created those elementary, middle school volcanoes where you stick the baking soda in and then you put the vinegar, that's the word, putting the vinegar in and it starts to bubble? What's happening? Well, the baking soda is the base and the vinegar is the acid. And when those two combine, you generate carbon dioxide gas. And that is an acid-base reaction. And so we have some definitions that we need to understand. Okay? It's called a Bronsted-Lowry acid base. Now, so let me write that down. We have Bronsted-Lowry. Okay. That has a signal through there, like that. So if we have a Bronsted-Lowry acid, all right, there is a definition to that. And a Bronsted-Lowry acid is a proton donor. Acids donate protons. If we have the same thing here, Bronsted-Lowry base, a Bronsted-Lowry base accepts a proton. So that's the definition. So with Bronsted-Lowry acids and bases, a proton is involved. And when I say proton, a proton is a hydrogen atom. So we have a hydrogen atom, and when we look at the nucleus of a hydrogen atom, we have one proton. And so we just call hydrogens protons. Now when we take a look at this definition, but look at it in a reaction scheme here, what we have is a general mechanism of how acid bases work. And I'm going to represent any base, okay, with the letter B. There's many, many different versions and variations of bases, but I need to represent all of those with a B and going to have a negative charge. So that's our base. And that base is going to react with an acid. And I'm going to represent an acid with a H, A. So A for acid. And Bronsted-Lowry acids right here have a hydrogen attached to them. And then we're going to have an equilibrium process here in which we are going to follow this definition using our curved mechanism arrows. So the lone pair on the base, right, is going to come and abstract that proton. So the base is going to come and form a bond with the hydrogen, and then the hydrogen acid bond is going to break. And when that breaks, what's going to be our product on this side? Well, these lone pairs right here are coming to form a bond with that hydrogen atom. So we have this. Do you see how that this lone pair, 2 electrons, are right there in that covalent bond? So we could honestly represent that covalent bond like this. And then we would have the 2 electrons in this bond. They're going to break and be added to the acid. So we'll put the lone pair there, and then that will become negatively charged. We don't represent covalent bonds like that, so we just have the single bond right there. Now let's go back to the definition here. Do you see how that the acid, let's write those here. So this is our acid, and this is our base. What is the acid doing? The acid is donating its hydrogen to the base. Because when we get to this side, or the right side of the equation, what do we have? This B has now accepted that proton. Now, on the left side of the equilibrium arrows, we are always going to have a base and an acid. Then on the right side, this B now, okay, becomes the conjugate acid. And this A minus is now going to be called the conjugate base. And I'm going to run out of room here. Conjugate base. So on the left side of the equilibrium arrows, it's just acid or bases. And on the right side, it's conjugate acids or bases. So we can see that the base on the left side turns into the conjugate acid. And then the acid on the left side turns into the conjugate base. And the reason why this is the case, okay, because look at this. These arrows right here mean equilibrium arrows. So we can have a forward reaction and a reverse reaction. And so in the reverse reaction, what do we have? We're following the same definition. A base accepts a proton. So this A minus is considered a conjugate base because its lone pair now can come and abstract that proton. And then this BH bond is going to break, putting the lone pairs back on the B, which you can see this going in this direction turns into the acid, and then the conjugate acid here turns into the base. So it's really, really important to understand what's happening with these mechanism arrows. When you have a base, bases have lone pairs that are going to be used to attack the hydrogen on the acid. And then that hydrogen bond, or this bond right here, has to break. And we take those 2 electrons in that bond and put them directly on top of the A, which we see right here. So it's very important to look at this mechanistically and see where the electrons are going. Okay, so now let's take a look at using this general formula here, let's take a look at some actual acid-base reactions so you can see how the general mechanism applies to some real-life examples. Let's take a look at water reacting with HCl. And this is an acid-base reaction. So what are the products going to be over here? Okay. Well, when we look at this, we have to make a decision. We have to say which one is the acid, which one is the base when we look at water and HCl. Oftentimes, you can determine which one is the acid or the base just by looking at their name. Remember in general chemistry, if you looked at this molecule right here, I've been calling it HCl, but what is its name? Hydrochloric acid. So that's the acid. And so I'm going to mentally or actually write it out and be like, hey, hydrochloric acid, that's my acid. And this is water. So if I've already found the acid, then this has to be, by default, the base. Now when we take a look at the Lewis structures of these two molecules and look at them a little bit more carefully, we realize that we have 3 lone pairs on that chlorine atom, and we have 2 lone pairs on the oxygen atom. Now that I've identified my base and acid, we follow this general mechanism. It tells us that we are going to find the base and use one of the lone pairs on that base to abstract the proton. Because bases are what? Proton acceptors, and acids are proton donors. So this acid is going to donate its acid to the water by this mechanism. And now what do I draw at the other end here? I just follow my mechanism arrows. It is showing me that this lone pair here is forming a bond with that hydrogen atom. So I just go, okay, if that's what it says it's doing, just like that. My hydrogen's still showing up on screen, perfect. Now, did I use that lone pair? No, that just stays right there. And I've been writing this a little too big. I'm running out of space here. Darn it. But what's left over here? I'll write it right below the water and kind of in this corner here. Plus, what do we have? This chlorine atom right here has these 3 lone pairs. So I'm just going to keep them there. But you can see that this covalent bond right here has 2 electrons in it. And where are those electrons going? I need to draw this arrow a little bit better because it needs to start from the center of that bond. And the 2 electrons in that bond are going to the chlorine. So I could say they're right there. Now I have to evaluate the formal charges. This chlorine is going to have a -1 charge. And this species right here is going to have a +1 charge. So this is called a chloride, and this is called the hydronium, one of the polyatomic ions that you've memorized in general chemistry. So here's our hydronium. And when we look at these 2 species, we need to now identify which one's the conjugate acid and which one's the conjugate base. Well, this species right here, the hydronium, came from water. And so that makes, by default, if that's the base, then that has to be the conjugate acid. And if this piece right here was the acid, then that makes that guy the conjugate base. And I ran out of space. And that is how you look at the, how you analyze acid-base chemistry. Now, could we take this side of the equation and go in the opposite direction? You bet we can. We need to find the base, which in this case is the conjugate base. We grab one of its lone pairs, grab a proton, and take the hydrogen-oxygen bond and put the electrons back. So when you look at the orange arrows, curved arrows, you can see we are going back over here. And that is an equilibrium process. So the forward reaction and the reverse reaction can happen. Let's take a look at another example here. So I'm going to erase that top one. So when we take a look at this reaction up top, and I tell you it's an acid-base reaction, obviously your job is to figure out which is the acid, which is the base. Now when we take a look, we see an oxygen with a negative charge and an oxygen with lone pairs. More often than not, the species, when you have two molecules that you have to determine which one's the acid or the base, the one with the negative charge is going to be the base. So we can say, okay, if we follow that rule here, we will call that the base. Now we can't use names to help us figure out which one's the acid or the base, because that's water, and that's an alkoxide, terbutoxide. So terbutoxide, water, those names don't really help us out determining if it's an acid or a base. But one trick is if it's negatively charged, can be a base. And so if we go off that premise or that idea that the negative charge is the base, then by default that makes that the acid. So we follow the same mechanism here. Same mechanism. We're going to take a lone pair off of the base, abstract a proton, and then that hydrogen-oxygen bond has to break. So what do we have at the end of the day? We have that plus these two atoms right there, so OH. So this oxygen atom already had those two lone pairs, but this hydrogen-oxygen bond is breaking and putting the electrons onto the oxygen, so I'll draw them right there. Yes, my blue arrow says to put them on the right side of the oxygen. It doesn't matter. Where all this blue curved arrow is saying is that the electrons here in this bond, oxygen-hydrogen bond, are going onto the oxygen. And where you place them on the oxygen doesn't matter. So we have these two lone pairs right there that were not used. So we have two lone pairs on the oxygen atom. Now we evaluate. What's the formal charges? Well, that was negative over here. Now it's neutral. It's neutral here. Now that guy goes negative. Okay. And so we need to identify which ones these are. So if that's the base right here, that makes that guy the conjugate acid. And then that would be the conjugate base. Now let's just stay consistent here. Let's go in the reverse. Well, we have to use the base to abstract the proton, and then the oxygen-hydrogen bond has to break, putting its electrons back onto the oxygen to give us this guy. All right. So let me reiterate this important concept. If you find yourself struggling with this idea of these blue curved arrows and these orange curved arrows and seeing what's happening. You have to be proactive and get help immediately because these mechanism arrows are never going away. They're in Orgo 1 till the end, Orgo 2, biochemistry. If you're taking chemistry courses, mechanism arrows is a thing. And get help early if you find that this is difficult or confusing, okay? Now in these last two examples, in both of the examples we used water. In this example we used water, and in the previous one we used water. But what was the difference? In this example, water was the acid. In the previous example, water behaved as the base. So you cannot just memorize that, hey, water is an acid. No, it can act as a base as well. So you have to look at the whole reaction to determine if water is going to behave as an acid or a base. And when a molecule can behave as an acid or a base, there's a special word for it. And it's spelt this way. Making sure I get it right. When a molecule can act as an acid or a base, it is called amphiprotic. And water is an amphiprotic molecule. Let's see, do we want to do another example? Let's do one more example just to make sure we can get this down pat, okay? This acid-base chemistry can be confusing. But what isn't confusing when you learn something for the first time? So if you're feeling a little confused right now and you're down on yourself, stop it. It's normal. It is a-okay. Okay, so what if I had something like this and treat it with what? Okay. And I'm starting to draw my molecules too big once again. So let's draw it a little bit smaller here. Okay. Now, as I'm writing out this problem, I'm giving you contextual clues as to which is the acid and which is the base. In this example, you could be like, okay, this molecule has some lone pairs there, lone pairs, lone pairs. This guy right here is a negative charge. So if we had to make a decision which one's the base, we would go to this guy because it has the negative charge. But we could also look at it based off of, what's the name of this guy? Well, that's hydroxide. And we learned from general chemistry that hydroxide is a strong base. It's always just a strong base. And we learned that in Gen Chem 1. But when we look at this molecule right here, can you name it? That's a carboxylic acid. Let's say you can't even use, let's say you're blanking on the IUPAC name. But you look at that functional group and you're like, hey, that is a carboxylic acid. So you know it's going to be an acid. Or if you take it to the IUPAC, you'd be like, hey, that's acetic acid. So you're like, that has to be the acid, all right? So that's going to be our base, and that's our acid. Now, I'm going to take a moment here to pause because I'm giving you contextual clues. Do you see how my HO bond right here, I show the bond? When I draw it like that, that's kind of like, hey, that's the acid. But on an exam or on a homework assignment, the molecule will be drawn like this. And now it's not so obvious which hydrogen is going to be the acidic hydrogen. But I'm giving you contextual clues to make sure you can see what's happening. Like that. Okay. So what's the mechanism? We're following this basic principle here. The base is going to come and abstract a proton, and the hydrogen-oxygen bond has to break. So can we draw what's on the product side? Well, the hydroxide grabbed the proton. So that's going to generate what? And watch this. I'm going to draw it in a different way now, and you will see this. I'm just going to draw it like this. It made water. Do you see how the hydroxide grabs the proton and becomes H2O? Plus there, the carboxylate. So which one is the conjugate base? Which one's the conjugate acid? That's going to be the conjugate acid, and that is the conjugate base. Now, when I want to do the reverse reaction mechanistically, how can I do that? Well, not how it's drawn. I'm going to have to now take this water molecule and just draw out the Lewis structures of it so we can show the proton transfer. I'll draw it like this time. Okay. Now, acid-base chemistry is the mechanism right here. That is called a proton transfer. We'll write that in orange here. So I can look at an acid-base reaction and call it a proton transfer. Because that's exactly what's happening. We are just transferring protons between two molecules. So if we do this proton transfer here, we would take a lone pair, grab a proton, and put it back. And that would be the reverse to get us here. Now this raises an important question, because when we look at a molecule, we are trying to find the acidic proton. So I'm going to take this molecule here, the acetic acid, and I'm going to draw it out below here and show you what you're going to be up against. All right. If I take that acetic acid and I have some generic base over here, all right, I've already established that this is the acid, okay, because of its name. But I notice that, hey, this is a carbon, and I'm going to draw it. And on that carbon, there's going to be what? 3 hydrogens. Why does the base not come and grab one of those hydrogens? Why have I been showing it grabbing this one? Well, to answer that question, it has to come to this idea called pKa's. pKa values. And pKa values are values that give you a number. And that number is going to tell you which proton is the most acidic. And we're going to jump into what pKa's mean, but just to show you here, this hydrogen right here has a pKa of approximately 5. And the pKa of this hydrogen right here has a pKa of approximately like 20. And once you understand what pKa values are and know their numbers, you could have your acetic acid right here You know you have a base. You know this is the acid, and then you ask yourself, well, which hydrogens? You go to your pKa tables, or you have them in your head, and you're like, 25. Well, I know that bases are going to go towards the proton with the smallest pKa value. And we'll talk about that in a minute. But that's the segue into learning pKas. The pKas are going to help us figure out the most acidic protons, so we know which ones to abstract when we do an acid-base reaction. Okay, so pKas. This is a review from general chemistry when you were looking at pKas a couple semesters ago. Let's say you take a generic acid and you treat it with some water. You're going to have an equilibrium process in which you have acid-base reactions going on. So you will have the hydronium plus the A minus. So what do we have here? This is our acid, that's our base, that's our conjugate acid, that's our conjugate base. So we have that equilibrium process. And how do we describe equilibrium? Well, that is what with the capital K with the subscript EQ for equilibrium. And the equilibrium for that process is going to be the concentration of the hydronium times the concentration of the conjugate base, all divided by the concentration of HA and the concentration of water. Remember that? Okay. So once you take some acid, dump it into water, and once equilibrium is reached, and that simply means that the net change in the forward direction and the net change in the reverse direction is the same. Okay? So we're at equilibrium. Now so this is our equilibrium here. But what's interesting is that once you reach equilibrium, the concentration of the water is going to be so large, so large that the concentration of water isn't going to influence the answer because it's more or less constant. Because there's so much of it, it doesn't change. Well, it doesn't change very much, okay? So we can look at this mathematically and say, hey, if this basically doesn't change, we can multiply it by both sides of the equation and get something that looks like this. So we could have equilibrium multiplied by the concentration of water, and that's going to equal the concentration of the hydronium multiplied by the concentration of the conjugate base divided by the concentration of the acid. Okay? Do you see how I just took this term right here? I multiplied it right here. And what you do to one side of the equation, you have to do to the other. And so that cancels with that guy. And now we have this equation that I will put in right there. That's what we have. But when we look at the equilibrium process through this equation right here, that has a new name. That is the Ka, or the dissociation constant of the acid. So the Ka, the whole purpose of that value is to show us how readily and easily this proton is donated. So if we have a very, very large number, okay? Well, it's just simple. If we have, let's just do a general thing here. What if we had an acid in orange and its pKa, sorry, its Ka is 10 to the 5. And then we had a different acid shown in blue, and its Ka is 10 to the 1. When we look at the Kas, which are these numbers right here, the larger the Ka, more acidic. Okay. So when you look at the orange versus the blue, which acid is the stronger acid? This guy. The orange one is the stronger acid. And when I say stronger acid, if you just look at the perspective of the A, and if the A could talk, this A right here is saying, take the proton. I don't want it. Get rid of it. Take it, take it, take it, take it. Whereas if this blue A could talk, it would be more like, yeah, you can take it. Never mind. No, I want it. But no, you can have it. And it's just like, it doesn't want to donate that hydrogen as readily as the orange one. That's what I mean by acid strength. Its ability to donate that proton. So what's going to happen is if we use Ka values here, those numbers can get rather large. And so what we could do to make the math a little bit easier to look at is you can manipulate the Ka equation to look at it in terms of pKa. So what you're going to do is once you've found your Ka, okay, and you have that value, let's say your Ka, let's see here. How do I want to show this to you? Let's see here. I'm reevaluating how I want to say this. Okay, so what I decided to do is just skip right to the equation. So we have the Ka right here, but we could also have something called the pKa, and that's going to equal the negative log of the Ka, like that. So now when we compare two acids, we could have, let's do a pink acid versus, let's say, the green acid. Now, if the green acid had a pKa, let's say 5. All right. And the pKa of the acid had a pKa of 1. Which one is the stronger acid in this case? Now with pKa values, these numbers right here are pKa's. It's the opposite of Ka's. The smallest number for pKa's is going to be the most acidic. So between these two acids, which one is the most acidic? It's going to be that one because it has the smallest pKa. And that just all has, and the reason for that is just because of the math here, okay? So I want to show you that with an example, okay? Let's see here. So let's take a look at some real acids here. Let's see here. Okay, so let's take a look at acetic acid. We have acetic acid there versus, let's take a look at phenol. And phenol looks like this. Okay. Now you can go to tables in your book. You could look it up on Google. You could say, what are the pKa's and Ka's of these two molecules? Okay, that's exactly what I did. And so for acetic acid, the Ka came out to be 1.76 times 10 to the negative 5. Okay. And its pKa equals 4.75. And when we look at the Ka for phenol, 1.6 times 10 to the negative 10. And then the pKa was 9.80. Right. Now, when we compare these two molecules, our goal here is to find out which one is the most acidic. That's the question I'm asking. So you could do it in two ways. You could look at the Ka's. So here's this Ka and this Ka. And you have to ask yourself with Ka's, largest number equals most acidic. And most of that's chopped off. But then, so let's just do that one first. So Ka's, the largest number is the most acidic. So 1.76 times 10 to the negative 5 is larger than 1.6 raised to the negative 10. All right. Now let's just make sure, if scientific notation is a little bit troubling for you, then you know it's something you need to review. Okay. So 1.5 times 10 to the negative 5 is larger than that Ka. And so we could say, hey, between these two acids, which one's the most acidic? Acetic acid. Acetic acid, way more acidic than the phenol. But then you can do it in a second way. And the second way is typically the method that chemists use to determine acidity. Okay? And that is the smallest. The smallest pKa is the most acidic. And so when we look at these two values here, 4.75 versus 9.8, that is clearly the smallest number, so that makes this the most acidic. Okay? So that's how you view it. Smallest numbers for their pKa's is the most acidic. So what if you had an acid with a pKa of -7 versus, let's say, another acid with a pKa of 1? What is the most acidic acid? Well, it's the one with the pKa with the smallest number, and that is the smallest number because it's negative. Okay? So overall, basically what you're doing is if you want, you can just draw yourself a number line. There's 0, there's 1, and where's -7? It's clear over here. So numbers furthest left on the number line are smaller. Okay, that's how you look at it. Now, I don't expect you to memorize the entire pKa table. Okay, that's a waste of your time. Would it be amazing if you could just put it all in there and it's just there forever? Yeah, that'd be awesome. But that's not likely. Not likely. So what I want you guys to understand are some general functional groups and their pKa's, and kind of memorize those. You don't have to memorize everything, but I do want you to understand the acidity of a few things, okay? So let's take a look at alcohols. I don't like that marker. Let's do a different one. You can look at alcohols, and alcohols typically have a pKa around 15 to 16. Are there some minor exceptions to that rule? Yes. We just saw it with phenol. Phenol had a pKa of around 9-ish. Okay, but generally speaking, alcohols have a pKa around 15 to 16. And if you can remember that number, it will serve you well. Okay? Now, what is the pKa of a hydrogen coming off of a sp3 carbon? That pKa is about 50, so not acidic at all. What if you had a hydrogen coming off of a sp2 hybridized carbon? You have a pKa of about 44. So a little bit more acidic, but not a lot. And then what if you had an alkyne? All right. Alkyne hydrogens are more acidic by a significant amount. All right. So those four right there are good to just have in your head at all times. Another good one to have is carboxylic acids. Carboxylic acids have pKa's around 5. If you can remember that number, it will serve you well. Let's see, what other functional groups come to mind that are important to just know? Alcohols, alkanes, alkenes, alkynes, carboxylic acids. Let's see, amines. Okay. Amines, they have pKa's in like the 30s, and our textbook here is saying around 38. Okay. So for right now, those are the pKa's that I would like you to just have memorized and off. Just you can answer them quick. So when in class, I'm like, what's the pKa of an alcohol? Boom, 15 every time. Carboxylic acids, 5. Yeah, those are the ones that I want you to just memorize. And as you progress in the course and looking at problems, you'll pick up other pKa's. And when you get into Orgo 2, you'll see different pKa's that are just good to know. But for right now, this is a good starting point. And with that, it looks like that's going to be the time for today. So if you have any questions or concerns, please reach out. I'll be happy to help.